All right, we've been talking about operation amplifiers and circuits in general, and really, I call these resistive circuits. Circuits with resistors and amplifiers and so on, they don't have memory, and we'll talk about that next week. But we've analyzed those quite a bit, and what we're doing now is we kind of know things, but I'm going to give you in the next lecture on Monday, I give you a whole bunch of additional examples on how to use what we know now. And then on Friday in a week, you can apply it yourselves. Okay, so in particular what we were talking about was input and output resistance. That's really nothing totally fundamental, but it's terribly useful to understand circuits. And this is an example that we did last time, where we used our understanding of input and output resistance to understand this circuit that then we found implements actually that famous negative resistor that you actually can build. So here is another example, something that we can learn about resistance and feedback and so on. It's extremely useful that as circuit designers you will use all the time if you choose that as a career path. You will find that very helpful. So here is an operation amplifier, and the operation amplifier, the triangle that I showed there, is always ideal, except in this case I introduce two non-idealities. The first one is I give it a finite gain. Okay? So here I say the gain is AV, so then the output voltage Vout is the difference between the positive and negative terminal by that open loop gain AV multiplied. Also something that in the office hour somebody asked, and I would like to say here again very clearly. If the gain of the operation amplifier is finite, then the two voltages at its input, they're not zero. Okay? It's only when the gain is infinite, then, this voltage here, it's zero, but only if we have negative feedback, and secondly, the operation amplifier is ideal, including it having infinite gain. Okay? So in this particular circuit, that will no longer hold. Okay? So, but obviously, I make it always very clear in an assignment or in an exam or so. Normally, the operation amplifier is ideal. That means gain is infinite, for example. And if something is not like that, then like here, I specify that. So here it has a gain AV, and I even marked it that the gain is finite. Okay, the other non-ideality that I introduced here is that ideally, operational amplifiers at their output, they're just like voltage sources with zero output resistance. Okay? So in this example, we're going to look what happens if the operation amplifier does not have a zero output resistance. And now, rather than introducing some kind of a new symbol and complicated description, I simply take my ideal op-amp and I add this resistor R1 here, and that models the finite output resistance. I take a source and I put the resistor in series with it, and now I have a real source that has finite output resistance, in this case R1. So what I want to know now is what that does to the overall output resistance. So if I look back into my operational amplifier, what is the output resistance? What does that mean? Well, a circuit having finite output resistance means basically that when I pull more or less current, then the voltage changes, right? It's just like a Thevenin equivalent, where R, or Thevenin, is not zero, like very often is the case. Then the voltage that we get from such a source, of course, depends on the amount of current we have. Okay? So here we want to evaluate what that is. And so basically what we want to find out is what is R Thevenin for this operational amplifier circuit here. How we do that? Well, we could, for example, apply a test source here, we test, and then we could vary that source and we could figure out what is the current I test that flows into the input of that amplifier. Okay? And then the ratio of these two quantities, of course, is going to be the output resistance. Okay? So whenever we do that, we have to make sure that the circuit is linear, and for that actually you have to turn off the source. So Vs will say yes.
But just in general, if you have a given circuit on a page, how do you tell if it's linear or not? It seems complicated to do.
That's right. So question whether a circuit is linear or not. All the circuits that so far we've looked at, they were always linear. And there are only very few examples where I will explicitly tell you that in this course where we have a nonlinear circuit. The Schmidt-Trigger that we looked at a couple of lectures ago, that was nonlinear behavior, right? Because suddenly the output of the amplifier started clipping because of the finite supply, and that was actually the behavior that we needed in order to implement the Schmidt-Trigger. Then digital circuits still not linear, but then we will look at other aspects. But generally, you can determine if the circuit is linear by looking at all the elements. Here, all the elements are linear, and consequently, the circuit is going to be linear. Right?
Is it a voltage source linear?
Yeah, voltage source is a little bit special. That's something that if you went to the sort of signals and systems, it's very important to have an accurate definition of linearity. Linearity really means that the output is proportional to the input. Well, if you have a source, then the output is actually proportional to the input plus the value of that source. And that's no longer follows that strict definition of linearity, and then superposition, for example, doesn't work anymore. But we get around this because we always, when we apply superposition, for example, we always say all the sources to zero except for one, and that's the input. And then the circuit is still linear. So I don't want to go too far into sort of the formal definitions of linearity and so on. We'll just use the sort of a common sense approach to help us analyze circuits. Yes?
Why do you say yes?
Okay, because what we want to measure is the ratio between V test and I test, okay, and then that slope. So we want to get something like that, and that slope is that resistance, right? And the way we are going to do that is we're going to apply a certain V test. We're going to measure what is I test, and the ratio then is the slope, right? Makes sense. Well, now if Vs was not zero, then this circuit would look different. The characteristic would look different. It would not go through zero, right? Even if we don't apply any voltage we test here, well, the output of our amplifier would be non-zero because of Vs not being zero. So the characteristic would, for example, look like the green line that I just showed. And then if we make again the same measurement, for example, here, now we look at the slope. Well, if we simply calculate the ratio of the two quantities, we get actually this slope here, which is not the correct slope. It's not the slope of the green line. Okay?
So is it basically the same thing that we do for our Thevenin, like you get rid of the volts?
Yes. There also, if you wouldn't make the voltage source zero, then really what you have to do is you have to. It's something in later circuit classes you will do that all along, and when it's nonlinear and so on, you have to do that. You would have to vary along this point here and then figure out the incremental slope. Then you still could get the right answer. But if you simply divide the two values, then that's true only if your characteristic goes through zero. And how do we make it that it goes through zero? Well, in a linear circuit, you can do that easily. Turn off all the sources. Okay? So that's really the deal behind it. Now, I'm not sure whether this was a really rushed explanation. I'm not sure whether everybody really totally understands the bottom of this. That's okay. That really is a little bit beyond EE40 material, so you will probably hear about that more and use it more. Small signal analysis and all sorts of stuff like that. We really don't do that here. Yes.
Oh, so where does R0 fit on the circuit?
R0 is looking back into the output. So we want to model this entire thing as a Thevenin equivalent, and I'm running out of space, but otherwise you have to put the Thevenin equivalent into your head. So we get the whole operation amplifier, which is a source, and it has some output resistance. Okay, that looks like a Thevenin model. Okay, so now we want to calculate what that Thevenin is. Okay, so first thing I just argued, we have to set the S equal to 0. Nothing tricky like that will be on the midterm, so don't worry about that if that's the thing. So now we need to somehow figure out what things are. So the I test is equal to, well, if we knew the voltage across this resistor, then of course we could figure out what I test is. It's the difference of these two voltages divided by R1, right? So what is the difference of these two voltages? Well, here, this is simply V test, right? And then at the output of the amplifier, well, I even marked that's a V out, okay? So then we need a second equation for V out. Now the amplifier here has a finite gain. So now I said that this is 0, so this is 0, then also this is 0, right? Because Vs is equal to 0, and no current flows into the positive terminal of the operation amplifier. Consequently, there is no voltage drop across RS. Hence, if Vs is equal to 0, the voltage at the input of the op amp is also equal to 0. Okay, so what about the other terminal here, the minus terminal? Well, that's just here we have V test. Well, then this is just a wire, so here we have also V test. So we have 0 minus V test, so that's minus V test times, well, the gain of this operation amplifier is AV. Okay? Now we have two equations we can solve these, and what we get is the ratio of V test over I test, which is equal to R Thevenin or R out of this operation amplifier with the loop closed, and that is equal to R1 over 1 plus AV. Okay? Wow, this is interesting. This is interesting. Apparently, if we didn't have any feedback, that is AV was 0, right? We didn't have an amplifier there. But then the output resistance would be simply equal to R1. That perfectly makes sense, right? If you have a source and then you have some resistance in series with it, well, that adds to the output resistance. But now look at what feedback is doing. Feedback kicks in and it divides the output resistance down by the gain of the feedback plus 1, actually. Okay? That's most interesting. So if I want to make a source with really that low output resistance, and is that a good thing? Yeah, of course, if it's a voltage source, a perfect voltage source has 0 output resistance. So if I want to make a source with really low output resistance, either I can somehow miraculously make a source that already has 0 output resistance, turns out that's really hard, that's basically not possible. Or alternatively, I can make one that has as low as output resistance as I can, and then I use feedback with high gain, and then the output resistance is divided down. And so that's actually what operational amplifiers use. When I told you that the output resistance of an ideal operation amplifier was 0, that really applied for the ideal operation amplifier. A real operation amplifier, the output resistance is not that low. It's several ohms to sometimes up to a kilo ohm. Okay? But then, because you apply feedback, the actual output resistance can be very small. For example, if this was 1 ohm and the gain was 1,000, well then, the output resistance with feedback is only a milliohm. And that's also, for example, what is inside the lab power supply that you use. The lab power supply, the circuits inside, they have an absolutely finite output resistance of probably an ohm or so, somewhere on the ohm, maybe a little bit less. And then they apply a lot of feedback with high gain to make it less than a milliohm. Okay? It's a very wonderful thing. We do that all the time. Turns out it's very, very difficult. Ultimately, all these circuits, they're made out of transistors. Well, the output resistance of transistors is not that small at all. Okay? And the way we can get really small output resistance, like in a regulator circuit, is we do this trick here. We apply feedback, and then the feedback divides down the output resistance. So what do we get out of this? Well, the first thing is, we had an example here, and we analyzed, and we got the result. So that's something that's useful. That could be on the midterm, right? And then you have to make such an analysis. And the other thing that's really great is we learned another nice property about feedback. We're not going to dive really deep into these properties of feedback yet in EE40, but they are important for circuit design, and you'll hear a lot more about them as we go along. Yes?
Did you set ES to 0? Don't you have another like half the problem until you finish?
Well, okay, so what I... Well, the gain of this circuit, the gain from... If the operation amplifier had really high gain, right? And then the gain from the Vs to the output here, now disconnect the output, would be, well, this amplifier is in what kind of configuration? It's unity gain, right? It's positive. It's a non-inverting amplifier, and it's simply the output is tied back to the negative input, so the gain is 1. We can see that easily. If now the gain is large, right, then this voltage here, I marked it already, this voltage is 0, so the input Vs and the output Vout, they're equal, right? So the overall model for this circuit, if we finally do draw it, the overall model for this circuit is Vs, and that RO that we just calculated, and that's the out here. Okay, that's the overall model for this circuit. The whole thing that I drew on the left side and messed up now really behaves just like that thing on the right side, like a voltage source value Vs and then output resistance R. Okay. Huh? Yes.
So we never really had a really ideal amplifier, right? Like
Never.
maybe it's not.
It doesn't exist. Ideal doesn't exist. As you find sometimes in the homework, right, in the assignment, sometimes I make a mistake. It's not ideal.
So basically, A is always a number, so it doesn't really matter what kind of amplifier you connect that voltage source to, right? Because like no matter what, it's going to give us like something really resistance, right?
Right.
So because like here you assume that AB is finite, which is always finite.
Yes.
Right? So it doesn't really matter what kind of amplifier we connect that voltage source to, right? Because always is going to give us like really small resistance. Does that make sense?
In practice, this resistor, yes, it ideally would be 0. It's not 0, but then the gain, it's not infinite, but it's high. So in the end, we end up with resistance, output resistances that are less than an ohm and often less than a milliohm and so on. So it plain doesn't matter. Then you get a little bit of an error. I'm not sure whether I understood your question, but when I analyze operational amplifier circuits, and I suggest you do the same, then I usually first assume that the operational amplifier is ideal. And then afterwards, if I have a reason to believe that afterwards what I usually do is I throw the whole circuit into SPICE, and in SPICE you have already seen that SPICE has all models for all sorts of real operation amplifiers available. Okay, or you can get it from the vendor. The actual model for the operation amplifier that you're using, that includes all its non-idealities, so the gain is only 50,000, well, that's somewhere in that model. Okay? So then I simulate my circuit with that model for the real operation amplifier, how it really behaves. But now if I see that the simulation gives a totally different result than my analysis, then first maybe I try, I stick in an operation amplifier that has a much higher gain. Okay, and then if there is agreement, then I know that the problem is the finite gain of the amplifier. If there is still not agreement, then I know the problem is that I've made an error in either my calculations or I put the circuit wrong into SPICE. Right? Okay? So anyways, then if I find that it's actually the finite gain of the operation amplifier that is the problem, then maybe I go and analyze the circuit much like we did here for finite operation amplifier gain. I look what the error is that it causes. I look whether I can accept that error, and if not, I find out some kind of a modification to the circuit, sometimes just getting an operation amplifier that has higher gain is closer to ideal, sometimes really modifying the circuit. For example, instead of having one operation amplifier that provides a gain of 1,000, I have two that each provides a gain of 30, and if I cascade it, I get 30 times 30, 900 gain. Things like that. Okay? Did I answer your question?
I was basically trying to kind of like, because like in real world you never have an ideal amplifier, right?
Yeah.
So like, you're always going to have like that equation always going to work, right? R1 over 1 plus A. So I was thinking like, no matter if it's ideal or not ideal, it's going to work, right? Like that.
Well, that's a little bit dangerous because this is now one particular circuit and a relatively simple one. You have seen on the quiz, right, the third problem, there was an op-amp and I made a big mess right around it. Turned out it didn't matter the mess, but anyways, there's so many different circuits that in general I need to warn you in EE40. Don't try to remember equations or so. Understand how to derive them, because I make a small modification to the circuit and then it's a similar equation but not exactly the same, right? And then it, of course, that's wrong. So that's why even I told you, even for voltage divider, more or less, maybe after a while you know it, but the way I use the voltage divider equation in my head, I immediately always know how the voltage divider works, and so kind of rewrite the equation every time. Yeah. Be careful. That's also why for the midterm one you won't have a cheat sheet. You fool yourselves if you think that the cheat sheet is going to solve it or help you. Okay? You really need to understand circuits to do well on the midterm or on that quiz also. I think you had a question.
So when you considering slides, I tried different op-amps, models that were available on the program, and they all gave you different results.
Yeah, exactly.
Which model do you recommend?
Well, you have to. So choosing operation amplifiers. Well, in the lab we use. I've chosen an operation amplifier for you, right? By reading the data sheet and figure out what we want to do with it, and said, oh, this is a good compromise. And the vendor donates it to us, so that was helpful too. But yeah, you need to get the model for the operation amplifier that you're actually using. And when you design circuits, well, you have to go over the data sheets and figure out which operation amplifier to use. Now, in EE40, this isn't that big a deal, even in the project or so. The stuff that we do, it's slow, it's not overly incredibly precise, our impedances are not unbelievably terribly high, and so on. So most operation amplifiers will do. But as you go on and you design more challenging circuits, then you really have to read these data sheets, and yeah, you will find that one operation amplifier has a very high gain, and but then it has a high offset voltage. In other words, what is the offset voltage? We never talked about it, but I always say that the difference between the two inputs of an operation amplifier should be zero if you have feedback, high gain feedback. It's actually not true. A small voltage appears that, depending on the op-amp, is anywhere from a few microvolts to a few millivolts. Well, in some applications it really doesn't matter. In most applications that we deal with in the lab here in E4, it just plain doesn't matter. That's why they tell you about it. But there are, of course, cases where a few millivolts, hey, that's the whole error, right? If I build a thermometer and the output of my transducer is only 1 millivolt per degree, well, if I have 2 millivolts offset, I have, right from there, I have a 2-degree error. Right. So, there is more. Hey, you know, I told you in the beginning, circuits is a lot of fun, and one of the reasons, of course, is that there is more to learn and play with, and I hope that just now we get sort of enough understanding that we can contemplate some of these problems, but let's not get too far in, not too deep. Otherwise, I mentioned already, I also teach 240, and I would love to teach that to you, but not today. Okay? So, well, I think this was actually a problem on the homework already, but let's look at this one. Did I cover all the questions? Okay, let's look at this one. This kind of fun, another view of input and output resistance. so what I want to do here is I want to build a circuit that takes some input voltage, let's say 4 volts. And then it produces voltages, half that, 2 volts, again half that, 1 volt, half that, half a volt, quarter volt, and so on. You may ask yourselves, why is this important? Well, it turns out that's a circuit that's terribly often used in analog digital converters and digital analog converters. So basically, those things that connect real devices to a computer. Let's say in your phone, when you're talking to your phone, hey, your voice isn't a digital signal, but your phone ultimately transmits a digital signal. So there needs to be a circuit in between that does the conversion. Well, and that's an A to D converter. And it uses, among many other things and many other features, it uses a circuit that can establish these voltage divisions. So what we want is a circuit that takes an input voltage and then produces that voltage over 2, over 4, over 8, and so on. Okay? All right, so let's take it for now just that we want to build that circuit. How are we going to do that? Well, let's say, actually, this should have called this V1. Huh? Here it's V1. So suppose that we have a voltage V1 and we want to divide it in 2. How are we going to do that? Yeah, a voltage divider, and we just make 2 resistors, both the same, and then this is really V1 over 2, right? No problem. Okay. All right, so now, if I want to divide this one again in 2, what can I do? Okay, if I stick another one like this right after it, what's the problem? What's going to happen if I simply were to take another board? Or would this be V2 over 2, the voltage here? No, actually, this would always be 2. Here is the voltage V2, right? And then we simply have a voltage divider, and so the voltage across this resistor here, of course, is V2 divided by 2. That will always be true, regardless of the current that's flowing. But there is something that is now messed up. What is it that is messed up now? Yeah, exactly. This one here is no longer V1 over 2. Why not? Well, because there is current flowing here. Okay? Okay, so now we can actually fix this problem by understanding input and output resistance. What is the... So forget... maybe... Okay, so let's see, what is the input resistance to this thing? Well, the input resistance, just the resistance that we see there is 2 resistors in series, right? So the input resistance is 2R, right? Okay? So if we want to connect another one of these, what we are really connecting to the next one is a resistance 2R. So what we did before was we connected that extra resistance, but we want that here we want that 0 current flows, right? So we are going to connect another resistor to R here. If we simply connect the same one, and then of course instead of having resistance R here, we have R in parallel with 2R. Okay? So how can we fix that? Well, we can break up this resistor R that's shown here. What did we do with R? We made 2 resistors of value 2R. What does this behave like? 1 resistor with value R. Right? But now comes the trick. This resistor I actually built. But this one here, the second one, is something else. What is the second resistor? Well, what I want to do is I want to cascade stages that divide by 2. They look like a resistor of value 2R, right? So I'm going to replace this resistor here with a whole stage like this. Okay? So what I do is I build the first stage that divides by 2, and I terminate it not with the resistor R, but with the resistor 2R, and then I presented another resistor here of value 2R. Right? So this thing here looking in here also is 2R, and I can make the same argument here, and so on. Ultimately, at the end, when I want to stop, I need to present the resistance of value 2R. So then in the end, I have to put the resistor 2R. It's one additional resistor 2R there. Okay? Yeah.
So what would be the voltage across the last one?
Well, every time it gets in, so this is V1 over 2, over 4, over 8, over 16. And I can replace this guy again by one of these, and then I can get to a 32, and so on. Okay? Yes? Well, whether this gives an error. So if this circuit here is perfect, if the values of the resistors are exactly the way we chosen, the way we indicate here, then you get absolutely no error. You can do this for as long as you want, and you always divide by 2 exactly. And our argument here sort of showed that you could also, of course, use, God knows, I wouldn't recommend it, but you could use node voltage analysis, and you'll find that you get exactly resistance voltage divided by 2 at every stage. Now, in practice, of course, when you actually make this, the value of the resistors R is not going to be all identical, right? They're going to vary a little. One is a little bit too big, the other one is a little bit too small, and yes, then you start getting errors here. So it depends on what you want to do. For 8 bits, you need about 1% active resistors. Okay, so circuit is used quantity, and then there are lots of much more clever tricks that you can make it. That's another thing that we're not going to talk about in 40, but that's a very common problem in electronics. Accurate circuits are expensive, right? Components which have very accurate values are expensive, and sometimes they're just not even obtainable. Even in these ICs that I told you, they cost thousands and sometimes millions of dollars. The components, they vary by several percent or so. So miraculously, it's possible to build circuits out of imprecise components, but build them in such a way that in the end, what you get is very precise. Okay? Right? So actually, we'll remind me in about a week or so, we'll talk about a voltage doubler that you can make very precise, even if the components that you have are not precise at all. But you can make, there's nothing precise in there, but in the end, you exactly get the voltage that is 2x the input voltage. Right? Yeah.
Can you express other mathematical theories or circuits?
Oh, I'm sure. So now, I'm not a mathematician, but I'm sure I actually first thought that this is a neat kind of thing, and I almost put it on the midterm and would have told you that make it a 1/3 or so. But then in the end I thought, well, maybe, not quite everybody gets it, and I found something else. But yes, you can now go wild and invent your own stuff, right? You had a question?
Is that error correcting codes or something? Like when you...
Okay, error correcting codes, very interesting topic, totally above my head. I don't use error correcting code when I make the circuits precise. Okay? Go take the whole sequence, you end up in my 247, and I'll tell you, dynamic element matching, all sorts of clever tricks or chopper stabilizations, and then you can make very precise circuits, even though what you have is, geez, nothing precise. Okay, so skills, well, what did we get here? There was really nothing new, right? The circuit that I showed you just on the page before this one here, of course you know how to analyze this. You can write a whole bunch of equations, maybe using node voltage method or so, and you can analyze this circuit, you will get the right result, which is just going to take a lot of time. What we really learned here was a little bit more insight, right? Circuits are not equations. circuits, they have some characteristics and behaviors, and if we can understand those well, then we can design clever stuff like chains of resistors that divide the voltage by a geometric series. Okay, so really the big thing that we got here was insight. And we already knew, of course, that the source, well, we can model it as a Thevenin and a Norton equivalent, and we did that again here. We also knew that any kind of a load, if it's linear, we can model it by a resistor, and that's what we did here again, right? The inverting amplifier, we modeled that by a resistor, and its value is just the resistance, the input of that inverting amplifier. So that kind of knowledge is not fundamental, but it's terribly helpful. If you want to design circuits, you need to see that and understand that, and so I encourage you to sort of look over these examples. I will have a few more, and we'll use that several times. And then there was also this kind of a thing of a buffer amplifier, right? We found that sometimes we need an amplifier not in order to get voltage gain, but we need an amplifier such that we don't pull so much current from the source. Because if we use a non-inverting amplifier, for example, then we can observe the signal without consuming any current if the amplifier is ideal. And for example, a voltmeter, of course, does that. Voltmeter, very important. The input resistance has to be extremely large, right? So a reasonable voltmeter a reasonable model for a voltmeter is a really large resistor. And the dBm that we have in the lab there, that resistor, you can look it up in the manual, happens to be 10 mega ohm. For some of them it's probably a little bit higher, and for others a little bit lower. Okay, so that's what this was about. So we just have enough time to look at one more example where we apply just the same understanding that we learned about, we apply to another circuit, and this example will give us two benefits. One of them is this thing called instrumentation amplifiers is actually something terribly useful, and so we'll learn about it. And the other thing is we actually learn how to analyze the somewhat, at first sight, somewhat complicated and tricky circuit with 3 operational amplifiers, and we analyze that, and it will take us 10 minutes. It will not be that difficult. So the sensors, we looked at this before, right? I don't need to repeat that. That's our strain gauge. Now, the problem of the strain gauge was that the output voltage was pretty small. You saw that in lab 2, right? Was it? Okay. So that output voltage is pretty small, and so obvious idea, go and add an amplifier. So here we have a sensor, and then put an amplifier here. We can give that some kind of a gain. Now what we would like this to be is that the out is equal to some factor, that probably should be large, times the sense voltage, right? That's what we would like it to be. But in reality, and I've shown you here the result, this is the output voltage, and that's the equation for it. Well, what we get is, well, if you look at the equation carefully, it's sort of it's a reasonable approximation of this thing here, but not a very good one. What's the problem? Well, the problem is that current flows into the amplifier, and that current upsets the value of VI. Okay? So how could we fix this situation? We want to put an amplifier there, but apparently we really don't want current to flow into our amplifier. How would we do that? Yeah.
You put a big resistor there.
Okay, we could try to put we could make these two resistors really, really big, and then maybe the current that would be flowing would be smaller. Huh? Yes.
Put a simple non-inverting op-amp from each point where we measure VI.
You mean like this?
Yeah.
Okay. Okay. So So he's got it right, right? So one solution would be we have the same amplifier as before, we have the same sensor as before, but in the middle we have these buffer amplifiers, and these buffer amplifiers, they do not provide voltage gain, but they have the ability to supply current while they don't take any current. And how would you build one of these things? Well, I'll tell you because we have to go a little quick. That's what this is, right? Okay? There is no current flowing into the input of this guy, and the input and the output voltage are the same, but of course the output can deliver current. In fact, the output is in zero, right? Okay? So now this is all right, but now we need 3 operation amplifiers, and it turns out that it's really not the most clever circuit. So it happens that there is a better solution. It's called instrumentation amplifier, and it's shown here. And the good thing about the instrumentation amplifier is that you can buy it. You can buy a little package, looks like an op-amp, but inside is this entire circuit. Okay? So then, instead of having to wire together 3 different op-amps, and imagine doing this in the lab, it gets a little bit tedious, especially if you need 5 of these, right? You get the whole thing in there. So now our problem is, well, what in the world is this mess with 3 amplifiers actually doing? Okay? So the circuit is a bit complicated, so how are we going to analyze this? So what do we want to know? Well, we want to know what is the output voltage as a function of the 2 input voltages here. Right? That's really what we want to know. What we want to know is the closed loop gain V out over VI1 minus VI2. And that's the closed loop gain of this instrumentation amplifier. That's the goal. So first of all, I almost forgot to say, well, we have to check, does it actually meet our first requirements? It shouldn't pull any current from our sensor. Right? Ultimately, of course, we're going to put our sensor here. I already abstracted that, made that sources. We want this current to be 0, right? And this one also to be 0, at least as long as the operation amplifier is ideal. And then, when we go and build it, well, we go and look at data sheets and we'll find some operation amplifiers, they pull actually a microamp, and others, they pull only a femtoamp, and so we use one that pulls a very small current only. Okay, so our circuit meets that requirement. Now, here the circuit is again. Now the question is, how are we going to analyze that? Well, if we knew the voltage VA and the voltage VB, if we knew these 2 voltages, then could we figure out V out? Well, that's just one amplifier now, right? And in fact, a while ago we already solved this circuit, right? That's the op-amp with the inverting input VA, and then there is also the op-amp with the non-inverting input VB. We could solve it, for example, using superposition. In fact, we did that already. If you go back to a few lectures, then you will find the solution of that. So the question is, how are we going to figure out what is VA and VB? Well, one thing that is very helpful now to determine is, of course, there is a current IA and a current IB flowing, right? So let's suppose that IA was a milliamp, whatever, right? 50. And then IA actually increases to 2 milliamp. Does VA change? Does VA depend on the value of that current? Why not? Yes, and the amplifier has.
It depends on the input of the.
Yes, but the amplifier. I think he said it. The amplifier has 0 output resistance. Right? All what you said was correct, but sort of the insightful answer that I wanted now is the output resistance looking back into the amplifier is 0. That means the voltage doesn't depend at all on how much current I pull out of that output of the amplifier. And now, if that doesn't matter how much current is flowing out, well then, I also could analyze the circuit, for example, for a current of IA equals 0 and IB equals 0. Well, if I do that, then my circuit gets a lot simpler. So I apparently can analyze this circuit. I get VA and VB, and then afterwards I analyze the other half of the circuit, this one here that we happen to have analyzed already, and I stick them together. Right? Those two results. Now, of course, you could solve this also using no voltage analysis or something. You will get the same result. But then you run out of time on the exam, right, or on the quiz or whatever it is. Plus, also, you can't design circuits if you don't understand them as circuits, but only as equations. I said that many times, so I hope you will believe me. Okay, so let's try to analyze this circuit. Well, the voltage at this node is, at this node here, hey, come on, it's VI1, right? The voltage at this node here is VI2. Okay, so that you all should be able to follow. Right? All right, so wake up. Now you have to pay attention. So then the question is, do we have negative feedback? Yes. Do we have negative feedback? Yes. Okay, so the operation amplifier is ideal, right? I didn't say anything else. So quiz question, what's the voltage here? That was actually a question on the quiz, right? I could have given you this circuit, it would have been bloody complicated, but actually the answer is trivial. What's the voltage there? VI1, right? So in other words, the voltage here is VI1, and we can make the exact same argument that the voltage here is VI2. Yeah? So, what's the current here? Over our gain, right? And now we can also figure out what the voltage is here, right? Because we know the current and we know the whole resistance, so we know that voltage. And if we then solve, what we get is VA minus VB over VI1 minus VI2, that is equal to 1 plus 2 or gain over R1. R1A and R1B are equal to R1. Okay? So the trick simply was to figure out what's the voltage here, and that was easy because there was negative feedback. And we know these two voltages, figure out the current, and now we know what is VA minus VB. And once we have that, we divide by VI1 minus VB. Okay? Very simple. Okay? I didn't show all the equations, but if you paid attention, then you can write them down yourselves now, and you will get this result. Okay, so there we have this solution. Here this is the other half of the circuit, and actually this half of the circuit V out over VA minus VB. I told you that we had solved this already, so go back in the lecture notes. What you'll find is minus R3 over R2. Okay? And then afterwards I simply have to put them together. I have this one here that has a gain of 1 plus 2 or gain over R1. And then I have the second one, this guy, that has a gain of minus, let me put the minus out there, R3 over R2. And that is therefore equal to V out over VI1 minus VI2. Okay, I promised we could solve this in 10 minutes. We actually have another 2 minutes, so are there any questions? Yeah.
Minus, this whole thing is an inverting amplifier? Or something?
That's right. That's right. And why is it inverting? Well, the first half is not inverting, right? These are two non-inverting amplifiers. But then the second part here, this one here, is an inverting amplifier. Now I could, of course, very easily change this whole thing into a non-inverting amplifier simply by flipping my connections of VI1 and VI2. Right? If I exchange these two wires, well, then I get a non-inverting amplifier. So the instrumentation amplifier can be used both as an inverting or as a non-inverting amplifier. But if you make the connections the way I showed here, then it is inverting. Also, another thing that generally these resistors are 1, 2, and 3. they're actually hardwired into the circuit. They're already on the chip that you're buying, and the only thing you have to do is externally supply this resistor or gain, and there we can set the gain anywhere between 1 and 100 or something like that. I think you had another question?
What did you say the second amplifier has Ethernet? Is that inverting amplifier?
Yeah, this, right, the
Second you said it's non-inverting.
okay, yes, that's right. It really calculates VB minus VA, right? Times some factor. Huh? And because I had not in my equations, I had not the VB minus VA, but VA minus VB, then I got the minus sign. Right?
No, the question was like the second amplifier. Why did you say that it's a non-inverting amplifier?
Oh no, this one is inverted. This one is inverted. This one provides inversion. This one doesn't.
Why is it inverting?
Why is it inverting?
Because you're going to both negative or positive.
Yes, but it's because I define this as my positive terminal. I simply, in my equations, I wrote VA minus VB, not VB minus VA. This is the positive terminal. Again, from here out here is negative. Right? If you just look at this, oops. I mean, you can do superposition to make this zero ground business, and then this looks like an amplifier where a resistor goes to the negative input terminal. We found that to be. I could put it down. I just trivial, but I'm running out of time. Any more questions?